Welcome everyone. In the previous video, we have presented the formulation for the electric and magnetic fields inside a rectangular waveguide filled with a ferrite slab, and this ferrite slab is biased by a magnetic field in y direction, while the propagation of the electromagnetic wave inside the waveguide in z direction. And this formulation has been ended by formulating the electric field Ey and Hz in terms of four unknowns, such that the field Ey in the region from 0 to C has a function, and from C to C plus T inside the ferrite medium has another function, and finally from C plus T to A has a third function, and from Ey we obtain Hz, and we said that to obtain the unknowns A, B, C, and D, it is required to apply the boundary conditions at the tangential boundaries between the air and the ferrite. So effectively, we have two boundaries, boundary at x equals C and boundary at x equals C plus T. And Ey at C from the side of the air equals Ey at C at x equals C from the side of the ferrite. In a similar way, Ey at C at x equals C plus T from the ferrite side equals Ey at x equals C plus T from the air side. So from these two boundary conditions, we can see that at x equals C, the value A sine Ka multiplied by C, which corresponds to the tangential electric field from the air side, would equal the value. Here we are going to apply x equals C, so the first term it would be 0. The second term it would be C plus T minus C, it would be sine Kf multiplied by T. So the electric field at x equals C in the ferrite, it would be C multiplied by sine K ferrite multiplied by T. In a similar way, at the second boundary at x equals C plus T, when x equals C plus T, this term it would be 0. So here x equals C plus T. C plus T minus C, it would be B sine Kf multiplied by T. B sine Kf multiplied by T would equal the tangential electric field in the air side in the third region. Here we are going to apply x equal C plus T. C plus T. So it would be D sine Ka minus C minus T, which is actually the distance D. So it would be D sine KAD. So we have already obtained two equations from applying the boundary condition that the tangential electric field at the air equals the tangential electric field at the ferrite. In a similar way, we are going to match the tangential magnetic field at the air to the tangential magnetic field at the ferrite at the interface. The tangential magnetic field in this case it is Hz. And as we have discussed in the previous video, Hz for x greater than 0 and less than C will be given by this equation. For x greater than C and less than C plus T, it will be given by this equation. And for C plus T less than x and x less than A, the Hz would be given by this equation. Now, at the boundary x equals C, the magnetic field in the left side it would be jka over omega mu naught cosine ka multiplied by c. And at the left side, where x equals c, it would be x equals c, so this sign it would be 0. So we have here, so by collecting the 4 equations, we have 4 equations in 4 unknowns. We can formulate the problem as a matrix multiplied by the unknown vectors or the unknown coefficients equals 0. So this equation would be valid only if the determinant of the matrix would be 0, and effectively the determinant of this matrix would be this equation, which corresponds to the eigenvalue equation for the waveguide in this case. Effectively, this eigenvalue equation or eigenfunction equation was the original equation which was used to find out the propagation constant beta in conventional waveguide. And if we are going to say that the value of kappa equals 0 and the value of mu equals mu naught, and in this case the value of k Ferrite equals the value of Ka, so we are going to obtain exactly the same eigenfunction for the rectangular waveguide. Alright, so we can do this test and apply any mu extraordinary as mu naught, any mu as mu naught, any kappa as 0, any kf as k air, where k air is the square root of or k air is the square root of omega squared mu naught epsilon naught minus the value of beta squared. Okay, so this is the eigenfunction, and the unknown of this eigenfunction is the value of beta. So it is required to find out the value of beta which satisfies this eigenfunction is 0, and this beta is effectively the propagation constant inside the rectangular waveguide loaded by the Ferrite slab. So we say that this is the eigenvalue equation to obtain the propagation constant beta. It is interesting here to note that this function is even function of kf, even function of Ka, but it is odd function of kappa beta. So if the value of kappa beta is changed in sign, we have another solution, and effectively beta here corresponds to the propagation constant, and kappa is coming from the permeability tensor of the ferrite medium. And it should be noted here that if the propagation constant or if the propagation direction is reversed, the value of kappa it would be negative. So if I am talking about forward propagation constant, I am talking about positive kappa. If I am talking about negative propagation constant or propagation constant in negative direction, I am talking about negative kappa. So this equation, we have two different equations, one for beta plus and one for beta minus. That's what we are seeing here. This transcendental equation for the propagation constant beta contains terms that are odd in kappa beta. These odd terms indicate that the resulting wave propagation will be non-reciprocal. It means that if I'm moving in positive z direction, I have a value for beta. If I'm moving in negative z direction, I have another value of beta. So these odd terms indicate that the resulting wave propagation will be non-reciprocal. Why? Since it's changing the direction of the bias field, which is equivalent to changing the direction of propagation. Assume that the biasing is still in y direction, but the propagation instead of being in positive z, it would be in negative z. This is effectively equivalent to I'm propagating in positive z direction, and instead of using positive y biasing, I'm using negative y biasing. So either I'm changing the direction of propagation and keeping the direction of the biasing, or keeping the direction of propagation and changing the direction of the biasing. Anything of this. So changing the direction of bias field, which is equivalent to changing the direction of propagation, will change the signs of kappa in the permeability tensor. And changing the sign of kappa will change the equation, the eigenvalue, the eigenfunction equation, which lead to different values of solution for beta. Effectively, these two solutions are identified as beta plus and beta minus. Beta for forward propagation in positive z direction, and beta minus for backward propagation in negative z direction. Where beta plus correspond to kappa positive and beta minus correspond to kappa negative. So these solutions are identified as beta plus and beta minus for positive bias and propagation in positive z direction, which has positive kappa, or negative z direction with negative kappa. So basically, if we have a rectangular waveguide loaded by a biased ferrite medium or ferrite slab, the propagation inside this waveguide, it would be non-reciprocal, meaning that if I'm moving from the point A to B, it will not be the same as if I'm moving from B to A. Right? In addition, if we included the effect of the losses, we can include the effect of the losses by allowing the value of omega naught to be complex, as we have mentioned before. So we are going to replace the value of the Larmor frequency of the ferrite media by from omega naught to be a complex omega naught plus G omega naught double dash, for example. And this will introduce complex susceptibility, and this will introduce complex value for kappa here and complex value for extraordinary permeability, and we will obtain complex value for the mu. So everything will be returned to complex. In this case, the propagation constant beta, in this case, it will be complex value. So it will be a real value which corresponds to the phase constant and imaginary value which corresponds to the attenuation. So we will have alpha and beta. Alpha is the attenuation and beta is the phase constant. So in this case, we have beta and we have alpha. And as we said, it is non-reciprocal. So we have beta plus and we have beta minus. Effectively, by using perturbation method or by applying Taylor series for very small value of t, we can get approximate solution for the value of beta plus and beta minus. And in this case, the difference between the propagation constant in the forward direction and the propagation constant in the backward direction, beta plus minus beta minus, it would be nearly 2k cutoff multiplied by the thickness t multiplied by kappa over A, which is the width of the waveguide, multiplied by mu multiplied by sine 2k cutoff multiplied by C, where the value of k cutoff is the cutoff frequency of the empty waveguide. If I'm talking about TE10 mode, k cutoff, it would be pi over A. If I'm talking about generally TEm0 mode, so k cutoff, it would be m pi over A. Actually, this can be simplified as 2k cutoff multiplied by kappa over mu multiplied by delta S over S, where delta S over S, it would be defined as the filling factor, which is actually the thickness of the ferrite slab to the width of the waveguide, T over A, multiplied by sine 2kc multiplied by C. C here, if we remember, is the distance from the wall to the Ferrite slab. So this is the difference between the forward propagation uh, constant minus the backward propagation constant as approximate 4. In a similar way, we can obtain the difference between the attenuation constant for the forward direction, or we can obtain the attenuation coefficient for the forward and backward direction, alpha plus and minus. Alpha plus and minus, in this case, it would be delta S over S, which is the filling factor, which is T over A, delta S over S, over beta naught, where beta naught is the propagation constant of empty waveguide, which is square root k naught squared minus k cutoff squared, multiplied by beta naught squared, multiplied by the imaginary part of the susceptibility in x directions, xi, xx dash, sine k cutoff multiplied by x. So the attenuation coefficient actually depends on where I'm talking about, where is the location with respect to the x. So if the value of x is different, I have different attenuation coefficients. Plus k cutoff squared xi double dash zz cosine squared k cutoff x minus or plus, according to I'm talking about the attenuation for the forward propagation or the backward propagation, minus or plus xi double dash, this it should be xz, because here the biasing in z direction, in y direction, so I'm talking about xi xx, xi zz, and xi xz. So this actually z, xi double dash xz k cutoff beta naught multiplied by sine 2 k cutoff x. This is actually the attenuation for the forward and backward direction, and it can be noted here that the attenuation coefficient in this case is not equal. So in the forward direction, maybe I have less attenuation than in the backward direction, and this property is quite useful in a very important microwave component, which is called microwave isolator. Microwave isolator is a two-port network which allows the electromagnetic wave to move from port 1 to port 2 with minimum attenuation. On the other hand, it moves from port 2 to port 1 with very high attenuation. This is called isolator, and effectively the non-reciprocity in the waveguide loaded by a Ferrite slab make this configuration is quite suitable to introduce a microwave isolator, and the microwave isolator will be discussed in a following video by using such ferrites. Now we have already completed the formulation of the eigenfunction for a rectangular waveguide filled by a Ferrite slab, and we obtained approximate solution for the propagation constant and the attenuation constant in this case, and we have concluded that the propagation in this case is non-reciprocal, so the propagation in positive z direction is not like the negative z direction. In the following video, we are going to examine another configuration. What will happen if I have two symmetric Ferrite slabs, such that instead of I have a single Ferrite slab oriented in one side, I have two symmetric Ferrite slabs inside the rectangular waveguide. That's what we are going to discuss in the following video. All right? Okay.